Improper integrals. Improper integrals over unbounded intervals. Suppose that f is continuous on the closed interval from a to infinity. We want to give meaning to the integral of f from a to infinity. We can do this by considering an arbitrary right endpoint b greater than a, integrating from a to b, and then taking the limit as b goes to infinity. So we define the integral from a to infinity of f of x dx to be the limit as b goes to infinity of the integral from a to b of f of x dx, provided the limit exists. And when the limit exists, we can interpret it as the signed area of the region with infinite length between the graph and the x-axis to the right of a. And we say that the improper integral converges if the limit exists and diverges if the limit doesn't exist. We immediately have a theorem that says that if the improper integral from a to infinity of f of x dx converges, then the limit as x goes to infinity of f of x must equal 0. In other words, for a convergent improper integral, the integrand must approach 0 as x goes to infinity. A useful equivalent statement is that if the limit as x goes to infinity of f of x is not 0, then the integral from a to infinity of f of x dx diverges. Think of this in the context of a positive function as indicated in the picture here. If the region between the graph and the x-axis does not become thinner and thinner as x goes to infinity, then there is no way that the area could be finite. Similarly, if f is continuous on a closed interval from minus infinity to b, we define the integral of f from infinity to b as follows. We think of an arbitrary left endpoint a less than b, integrate from a to b, and take the limit as a goes to minus infinity. So the integral from minus infinity to b of f of x dx equals the limit as a goes to minus infinity of the integral from a to b of f of x dx, provided the limit exists. And we speak of whether the limit exists in terms of the convergence or divergence of the integral. Also, if the limit as x approaches minus infinity of f of x is not 0, then this improper integral diverges. It's now a short step to defining the integral from minus infinity to infinity in the case where f is continuous for all x. We simply cut the integral in two by integrating from minus infinity to 0 and adding the integral from 0 to infinity, and the choice of 0 is completely arbitrary here. And this improper integral converges if and only if both of the improper integrals on the right side here converge. Before we do some example computations, let's talk a little bit about the fundamental theorem of calculus and notation in the context of improper integrals over unbounded intervals. Suppose that little f of x equals capital F prime of x for all x greater than or equal to a. In other words, capital F of x is an antiderivative of little f of x. Then, the integral from a to infinity of f of x dx is by definition the limit as b goes to infinity of the integral from a to b of f of x dx, and since capital F is an antiderivative of little f, this is going to be the limit as b goes to infinity of capital F of x evaluated from a to b. So this is the limit as b goes to infinity of f of b minus f of a, but the second term minus f of a does not involve b, so we're only taking the limit as b goes to infinity of the first term. So we may as well simply write this as the integral from a to infinity of f of x dx equals capital F of x evaluated from a to infinity, where we understand this to mean the limit as x goes to infinity of capital F of x minus capital F of a. In other words, an evaluation at infinity is to be understood in the sense of a limit as x goes to infinity. Similarly, if little f of x equals capital F prime of x for all x less than or equal to b, then the integral from minus infinity to b of little f of x dx equals capital F of x evaluated from minus infinity to b, meaning capital F of b minus the limit as x goes to minus infinity of capital F of x. Also, if little f of x equals big F prime of x for all x, then the integral from minus infinity to infinity of little f of x dx equals by definition the integral from minus infinity to 0 plus the integral from 0 to infinity. The first of these equals big F of x evaluated from minus infinity to 0, and the second term is big F of x evaluated between 0 and infinity. Now when we do these evaluations, the first term gives us a big F of 0, and the second term gives us a minus big F of 0, so the only thing that remains here are these limits. The limit as x goes to infinity of big F of x minus the limit as x goes to minus infinity of big F of x. And so in this case as well, it makes sense to use this notation, capital F of x evaluated between minus infinity and infinity, where we only need to be aware that evaluation at plus or minus infinity should be interpreted as limits. Examples. Let's compute the integral from 1 to infinity of 1 over x cubed dx. Note that if this integral converges, then we can interpret it as the area of the shaded unbounded region under the graph to the right of 1. The integrand is x to the minus 3, so we antidifferentiate, getting minus 2 times x to the minus 2, and we'll evaluate that from 1 to infinity. Evaluation at infinity means take the limit as x goes to infinity of minus 2 over x squared, and then we subtract the value of minus 2 over x squared at 1, which is negative 2. Now as x goes to infinity, minus 2 over x squared approaches 0, and so we get 0 minus negative 2, or 2. Another example, the integral from 1 to infinity of 1 over the square root of x dx. Here's the picture. If this integral converges, then we can interpret it as the area under the graph to the right of 1. Notice that the integrand does approach 0 as x goes to infinity, but it does so much more slowly than 1 over x cubed does. Our integrand is x to the minus 1/2 power, so we antidifferentiate, getting 2 times x to the plus 1/2 power, and we evaluate from 1 to infinity. So we take the limit as x goes to infinity of 2 times the square root of x, and subtract the value at 1, which is 2, but the limit as x goes to infinity of 2 times the square root of x equals infinity, so this integral diverges, and because of the particular way it does diverge, it makes sense to say that its value is infinity. Let's look at the general case here of the integral from 1 to infinity of 1 over x to the pth power for positive p. Each of the last two examples were of this type. If p is not equal to 1, then we compute as follows. Since the integrand is x to the minus p, an antiderivative will be x to the minus p plus 1 divided by minus p plus 1, and so we evaluate this between 1 and infinity. Factoring out 1 over 1 minus p, we have 1 over 1 minus p times the limit as x goes to infinity of x to the 1 minus p minus the value of x to the 1 minus p at 1, which is 1. So now let's see what we get for different values of p. What happens here is all about the exponent 1 minus p. If 1 minus p is negative, the limit will be 0, and the improper integral will equal 1 over 1 minus p times minus 1, or 1 over p minus 1. 1 over p is negative when p is greater than 1, so we have that the improper integral converges and equals 1 over p minus 1 when p is greater than 1. On the other hand, if the exponent 1 minus p is positive, then the limit as x goes to infinity of x to that power will be infinity. This tells us that the improper integral diverges to plus infinity when p is less than 1. Now what about the case of p equals 1? Then our antiderivative is the natural log of x, and evaluating between 1 and infinity means taking the limit of natural log of x as x goes to infinity and subtracting the natural log of 1, which is 0. But we know that the natural log approaches infinity as x goes to infinity, so the improper integral diverges to infinity when p is equal to 1. So now we have that the integral from 1 to infinity of 1 over x to the p diverges when p is less than or equal to 1. Let's remark here that the left endpoint 1 is only important to the value we get when the integral converges. The answer to the convergence or divergence question remains the same if that left endpoint is any positive number. Now let's look at a couple more examples. Let's compute the integral from 0 to infinity of e to the minus x over 3 times cosine x dx. If this improper integral converges, then we can interpret its value as the signed area between the graph and the x-axis to the right of x equals 0. We can antidifferentiate e to the minus x over 3 times cosine x by integration by parts, but for the sake of brevity here, let's just assume that we've done that. The simplified result will be 3/10 times e to the minus x over 3 times 3 times sine x minus cosine x. So we evaluate this antiderivative between 0 and infinity. We'll factor out 3/10 and write this as 3/10 times the limit as x goes to infinity of e to the minus x over 3 times 3 sine x minus cosine x minus the value of that at 0, which is e to the 0 times 3 times sine of 0 minus cosine of 0, which ends up being a negative 1. Now, since the factor 3 sine x minus cosine x is a bounded function, the e to the minus x over 3 factor here causes the limit to be 0. So we have 3/10 times 1 for 3/10. Another example. The integral from minus infinity to infinity of dx over 1 plus x squared. If this improper integral converges, then we can interpret its value as the area under the graph of 1 over 1 plus x squared over the entire real number line. The integrand is an even function, so symmetry tells us that this integral will be equal to 2 times the integral from 0 to infinity of 1 over 1 plus x squared dx. Since 1 over 1 plus x squared is the derivative of the inverse tangent of x, we have 2 times the inverse tangent of x evaluated from 0 to infinity. This is 2 times the limit as x goes to infinity of inverse tangent of x minus the inverse tangent of 0, which is 0. Now, as x goes to infinity, the inverse tangent of x approaches pi over 2. So this equals 2 times pi over 2, or pi. So the area of the shaded blue region here is exactly the same as the area inside the unit circle. Now let's look at a second type of improper integral, the improper integral of an unbounded function over a bounded interval. Suppose that f is continuous on the half-open interval consisting of numbers greater than a and less than or equal to b, and that f is unbounded as x approaches a from the right. This will be the case, for example, if the limit of f of x as x approaches a from the right is plus infinity, resulting in a vertical asymptote at x equals a as indicated in the figure. Then we define the integral from a to b of f of x as follows. Let c be an arbitrary number between a and b, compute the integral from c to b, and take the limit as c approaches a from the right. That is, we define the integral from a to b of f of x dx to be the limit as c approaches a from the right of the integral from c to b of f of x dx, provided that the limit exists. We say that the improper integral converges if the limit exists, and diverges if the limit doesn't exist. We can interpret the value of a convergent integral of this type as the signed area of the unbounded region between the graph and the x-axis between a and b. Similarly, if f is continuous on the half-open interval consisting of numbers greater than or equal to a and less than b, and if f is unbounded as x approaches b from the left, again, we think of an arbitrary c in the interval, integrate from a to c, and let c approach b from the left. So we define the integral from a to b of f of x to be the limit as c approaches b from the left of the integral from a to c of f of x dx, provided that the limit exists, and we speak of the existence or non-existence of the limit in terms of the convergence or divergence of the integral. Example. Let's compute the integral from 0 to 1 of 1 over the cube root of x dx. Here's the graph of the function on the interval 0 to 1. If the integral converges, we can think of the value as the area of this unbounded region. Since the integrand has a vertical asymptote at the left endpoint, this integral equals the limit as c approaches 0 from the right of the integral from c to 1 of 1 over the cube root of x dx. The integrand is x to the minus 1/3, so an antiderivative is 3/2 x to the 2/3 power. Now let's pull the constant factor 3/2 out front and evaluate x to the 2/3 between c and 1, and we have 3/2 the limit as c approaches 0 from the right of 1 minus c to the 2/3 power. Now clearly c to the 2/3 approaches 0 as c approaches 0, and so we have 3/2 times 1 equals 3/2. Another example. Let's compute the integral from 0 to pi over 2 of tangent x dx. Now this is indeed an improper integral because the tangent function has a vertical asymptote at pi over 2, and that's our upper limit of integration. So by definition, this is the limit as c approaches pi over 2 from the left of the integral from 0 to c of tangent x dx. Now recall that an antiderivative of tangent x is the natural log of the absolute value of secant x. We don't need the absolute values here because secant x is positive for x between 0 and pi over 2. So now we have the limit as c approaches pi over 2 from the left of the natural log of secant of c minus the natural log of secant of 0. But secant of 0 is 1, and the natural log of 1 is 0. Now, as c approaches pi over 2 from the left, secant of c approaches plus infinity, and so the natural log of secant c will also approach plus infinity, and so our improper integral diverges, and we can say that it equals plus infinity. So the shaded region under the graph here does not have a finite area. Some remarks with regard to the fundamental theorem of calculus and notation. We can use our usual notation for the evaluation of an antiderivative between integration limits if we simply let capital F of x evaluated between a and b be interpreted in terms of appropriate one-sided limits. That is, f of b minus the limit as x approaches a from the right of f of x in the case where the integrand is unbounded as x approaches a from the right, the limit as x approaches b from the left of f of x minus f of a in the case where the integrand is unbounded as x approaches b from the left, or even the limit as x approaches b from the left of f of x minus the limit as x approaches a from the right of f of x in the case where the integrand is unbounded near both endpoints. In fact, it does no harm to think of evaluation between a and b in these terms in all cases, even when the integral is not improper. With this in mind, the calculations in the preceding examples now look like this. The integral from 0 to 1 of 1 over the cube root of x dx is equal to 3/2 times x to the 2/3 evaluated from 0 to 1, where since the integrand is unbounded near the left endpoint 0, we interpret this as 3/2 times 1 minus the limit as x approaches 0 from the right of x to the 2/3. That limit is 0, and so we end up with 3/2. The integral from 0 to pi over 2 of tangent x dx equals the natural log of secant x evaluated between 0 and pi over 2. Now, since the vertical asymptote is at the right endpoint pi over 2, this becomes the limit as x approaches pi over 2 from the left of the natural log of secant x minus the value at 0, which is 0. And that limit is plus infinity. So the point here is really very simple. We can use our usual notation for the evaluation of an antiderivative between endpoints, even in the case of this type of improper integral, if we simply interpret evaluation as the taking of a limit when necessary. Now let's look at a couple more examples. Let's compute the integral from 0 to pi over 3 of sine x divided by the square root of 2 cosine x minus 1 dx. Let's first check what's happening with the integrand at each of the endpoints. At x equals 0, the value is 0, but at x equal to pi over 3, the denominator is 0 because the cosine of pi over 3 is 1/2. In fact, the limit as x approaches pi over 3 of the integrand is equal to plus infinity. And here's what the graph looks like. If this improper integral converges, then it will tell us the area of the unbounded region under the graph. Now to compute the integral, let's make a substitution. We'll let u equal 2 cosine x minus 1, which makes du equal minus 2 sine x dx. So the sine x dx in the integral becomes minus 1/2 of du. We'll also translate the limits of integration. When x is 0, notice that u is equal to 2 minus 1, or 1, and when x is pi over 3, u is equal to 0. So we have the integral from 1 to 0 of minus 1/2 du over the square root of u. Now, since we're integrating from right to left there, from 1 to 0, and we have a minus sign, let's turn the limits of integration around and get rid of the minus sign as well as pull 1/2 out front. Now notice that we have a different improper integral to compute. The integrand here has a vertical asymptote at u equal to 0. So let's anti-differentiate. We end up with 1/4 of the square root of u, and we evaluate that from 0 to 1. And so the value here is going to be 1/4 of 1 minus the limit as u approaches 0 of the square root of u, which is just 0, and so this equals 1/4. Another example. Let's compute the integral from 0 to infinity of e to the minus x dx divided by the square root of 1 minus e to the minus 2x. This example actually covers both types of improper integral. Notice that the upper limit is infinity, but also notice that the denominator is 0 when x is 0, and in fact the limit of the integrand as x approaches 0 from above is plus infinity, and this is what the picture looks like. Now we're going to do a substitution to handle the antidifferentiation, so let's go ahead and do that and see what happens to the integral. We'll let u equal e to the minus x, which makes du equal minus e to the minus x, and so e to the minus x dx becomes minus du, and the denominator in the integrand becomes the square root of 1 minus u squared. We'll translate the limits of integration. When x is 0, u is 1, and as x goes to infinity, u approaches 0, so the limits of integration become 1 to 0, and the integrand is 1 over the square root of 1 minus u squared times minus du. Now again, we're integrating backwards from right to left, and we have a minus in front of the du, so let's switch that around and get rid of the minus sign. Notice that this particular substitution has made both of the endpoints finite, and the integrand now has a vertical asymptote at the right endpoint, u equals 1. Now we should recall that 1 over the square root of 1 minus u squared is the derivative of the inverse sine of u, and so we have the inverse sine of u evaluated between 0 and 1. So this equals the limit as u approaches 1 of the inverse sine of u, or pi over 2, minus the inverse sine of 0, which is 0. Let's now consider the general problem of the integral from 0 to 1 of 1 over x to the p power dx, where p is positive. This is an improper integral because the integrand approaches infinity as x approaches 0 from the right. Now, if p is not equal to 1, then we do the antidifferentiation with the power rule. Since the integrand is x to the minus p, we get 1 over minus p plus 1 times x to the minus p plus 1, and that's evaluated between 0 and 1, where the evaluation at 0 is in terms of the limit as x approaches 0 from above. So we get 1 over 1 minus p times the value at 1, which is 1, minus the limit as x approaches 0 from above of x to the 1 minus p. So now let's see what happens. Everything depends on the exponent 1 minus p inside of the limit. If the exponent is positive, then that limit is 0, and so the integral equals 1 over 1 minus p. Now 1 minus p is positive precisely when p is less than 1. And if the exponent is negative, which happens if p is greater than 1, then that limit does not exist. So if p is greater than 1, we actually get infinity here. Now let's look at the case of p equals 1. The integral from 0 to 1 of 1 over x dx is equal to the natural log of x evaluated from 0 to 1, which is equal to the log of 1 minus the limit as x approaches 0 from the right of the natural log of x. Now log of 1 is 0, but that doesn't matter because the limit as x approaches 0 from the right of the natural log of x is minus infinity. And so we end up getting plus infinity here. And so this improper integral diverges to infinity when p is greater than or equal to 1. Now notice that this is just the opposite of what happened with the integral from 1 to infinity of 1 over x to the p dx, which diverged when p was less than or equal to 1 and converged when p was greater than 1. But in both cases, we have divergence when p is equal to 1. So let's think about both problems at the same time here. Let's look at f of x equal to 1 over x to the p, where p is positive, and think in terms of areas under the graph. If p is between 0 and 1, then we've learned that there's an infinite area to the right of 1 and a finite area between 0 and 1. When p is equal to 1, we've learned that we have an infinite area to the right of 1 as well as an infinite area between 0 and 1. And when p is greater than 1, we have a finite area to the right of 1 and an infinite area between 0 and 1. Let's finish up here with a brief discussion of a comparison test for convergence. Let's let the integral sign with the subscript I denote improper integration over an interval I, where that interval might be bounded or unbounded. And let's suppose that f and g are continuous functions on I, with 0 less than or equal to f of x less than or equal to g of x for all x in I. Then, if the integral over I of g converges, then so does the integral over I of f. In fact, we can also say that the integral over I of f is less than or equal to the integral over I of g. And if the integral over I of f diverges, then so does the integral over I of g. Now let's look at an example. Consider the integral from 1 to infinity of 1 over x plus the square root of x dx. Our integrand here is 1 over x plus the square root of x. Now we want to do one of two things. We either want to find a function that's greater than or equal to this function on the interval 1 to infinity whose integral converges, or find a positive function less than or equal to this function on the interval 1 to infinity whose improper integral diverges. Now let's note that for x greater than or equal to 1, x plus the square root of x is always less than or equal to x plus x, or 2x. Therefore, 1 over x plus the square root of x is greater than or equal to 1 over 2x, and that's a positive function for all x greater than or equal to 1. And we also know that the improper integral from 1 to infinity of 1 over 2x dx diverges, since the integral from 1 to infinity of 1 over x diverges. So we can now conclude that the integral from 1 to infinity of 1 over x plus the square root of x dx diverges. Now let's look at one more example. Consider the integral from 0 to infinity of 1 over the square root of x cubed plus x dx. We'd like to determine whether this improper integral converges or diverges. Now let's first notice that not only is the interval unbounded, the integrand has a vertical asymptote at x equals 0. So let's break the integral up into two pieces. Let's look at the integral from 0 to 1 and the integral from 1 to infinity. The integral from 0 to infinity will converge if and only if both of those two pieces converge. Now let's consider the first integral on the right, the integral from 0 to 1, and let's notice that the integrand is less than 1 over the square root of x when x is between 0 and 1. In fact, that's true for all positive x. And fortunately, we know that the integral from 0 to 1 of 1 over the square root of x dx converges, since that integrand is 1 over x to the p, where p is less than 1. Therefore, the integral from 0 to 1 of 1 over the square root of x cubed plus x dx converges. Now let's look at the integral from 1 to infinity. Now here we don't want to compare with 1 over the square root of x, because the integral from 1 to infinity of 1 over the square root of x diverges. But we can say that 1 over the square root of x cubed plus x is less than 1 over the square root of x cubed for all x greater than or equal to 1. And in fact, that's true for all positive x. Now 1 over the square root of x cubed is 1 over x to the p, where p equals 3/2, which is greater than 1, so we know that the integral from 1 to infinity of 1 over x to the 3/2 dx converges, and so therefore the integral from 1 to infinity of 1 over the square root of x cubed plus x converges. So now, since both of these integrals converge, we know that the integral from 0 to infinity converges. Now here's a picture to illustrate this. The blue graph is the graph of 1 over the square root of x, and the red graph is the graph of 1 over x to the 3/2. Notice that the graph of 1 over the square root of x cubed plus x lies underneath both of those curves for all positive x.